Welcome everyone, welcome back to lecture already 5 of this course in quantum optics. So today we will basically finish with the first long chapter that we have been studying, which is about the quantization of the electromagnetic field and harmonic oscillator states and so on. And maybe if we have time, then we will start with the quantum theory of matter, and in particular, a bit of atomic physics. But for now, what I want to do is just remind you a little bit of where we are and what we did in the last part of the last lecture. So let me just go to the beginning of coherent states. And in particular, let me just remind you very quickly that coherent states can be defined essentially as the displacement operator acting on the vacuum state, okay? They have many interesting properties. So the first property is that they are eigenstates of the annihilation operator, and on the right, and then left eigenstates of the creation operator. And they are parameterized by a single complex parameter that is related somehow to real parameters x and p, which play the role of phase space variables in the displacement operator that we studied before. So what we saw as well is that these are Gaussian states, and these are Gaussian states whose Wigner function is essentially the one of vacuum, but displaced to the position that we chose with the displacement, okay? With 2 times the imaginary part in the momentum and 2 times the real part in the position of this parameter alpha. Then I quickly told you something very interesting about them, which is that just like vacuum, they are rotationally invariant around the mean, okay? Meaning that any quadrature that you define in any direction of phase space, for example, a rotation of phase space whose axes are rotated by an angle phi with respect to the original positional momentum, all of them have a variance equal to 1, and therefore the Wigner function is really like a circle, or like a circle of uncertainty. Then we defined a general quadrature in a direction phi as x phi, and the corresponding momentum as p phi, which is actually just x phi, but changing phi by phi plus pi over 2, okay? So this is one thing that we saw. And then we saw how coherent states allow us to define something very important, as we will be discussing even more today, which are the amplitude and phase properties of the electromagnetic field, or in this case of just a single harmonic oscillator. And in particular, the location of this coherent state defines an amplitude, which is just the distance to the origin, and the orientation of this circle, or where it is in phase space, defines an angle, like a phase, which is phi, okay? And these two things, so this amplitude and this phase, are precisely the amplitude and phase that we would measure in an experiment, so classical or quantum experiment, for the average, let's say, of the amplitude and phase as we expect. But what's important is that once we are able of defining an amplitude and a phase, then we see that the fluctuations in the direction of the amplitude, or the fluctuations in the direction of the phase, okay, so delta mu and delta phi, these are related to fluctuations of some quadratures, x phi and p phi, that are defined with the phase of the oscillator, so the phase of the coherent state of the oscillator, and this we call the amplitude quadrature and the phase quadrature, because as I said, the amplitude fluctuations are directly proportional to the fluctuations or the uncertainty of the amplitude quadrature, while the phase fluctuations are proportional to the uncertainty of the phase quadrature. Okay, this we will talk a little bit more about it today. So then also very quickly, we saw a representation of coherent states in terms of the Fock basis, so the quanta basis. And what we saw is that the distribution of quanta in a coherent state follows a Poisson distribution of this of the absolute value of this parameter alpha. And this Poisson distribution looks very interesting. So for alpha smaller than 1, it's maximum at 0. But when alpha is larger than 1, it gets a maximum outside of 0. And when alpha is large enough, then it just becomes something similar to a Gaussian, like we know, with a well-defined peak and with a width that goes as the absolute value of alpha, while the peak goes as alpha squared. So this means that essentially the average of quanta is alpha squared, while the fluctuations of quanta are alpha. And this is very important, as I will tell you in a second why. But before that, we also saw that essentially coherent states overlap. Okay, so their overlap is not 0, but it decays exponentially with their distance in phase space. And we also saw that they form a resolution of the identity. Okay, and in the moment that we know that we have a set that forms a resolution of the identity, we know that we can use it to represent things. Okay, and in particular, because they overlap, so they are not orthonormal, okay, then they form a basis of the Hilbert space, but what we call an over-complete basis, okay? We have more vectors than we need in order to span the identity, okay? We know that the identity can be spanned just with, for example, Foxtails, which form an infinite set, but a discrete infinite set. And this is not the case for coherent states. Okay, then I remind you also that we developed a Gaussianity criterion based on coherent states, and the criterion is very simple. If I give you any state, rho, any state, and then you compute the expectation value of the state in a coherent state, a generic coherent state with amplitude mu, then rho is a Gaussian state if and only if you can write that as the exponential of a function that is at most quadratic in mu, okay, in the amplitude of the coherent state. So we proved it very easily, and we will use that today. And then finally, and this is where we stopped essentially, so we will start here today. What we did is discussing something very important about coherent states, something I like very much about them, which is that I find them the best bridge between quantum and classical physics. And why is this? So the reason is the following. So I remind you that what we discussed initially is that quantum physics and classical physics seem completely different, like radically different. It looks impossible to make a reconciliation between them because quantum mechanics predicts quantization of the energy and undefined trajectories in phase space, and classical physics is completely the opposite. It predicts a continuous energy spectrum, and it predicts well-defined trajectories. So who is wrong? Do we have some kind of connection? All the classical physics we have been doing, it's not the right thing to do. What happens? So, well, we saw that actually there is a reconciliation, or I told you that there is a reconciliation through coherent states with large amplitude, okay? And the reason for this is the following, that at the end of the day, when we say, let's go to the classical limit, in quantum mechanics, what this means is that we want to find a set of states or a state of our system that predicts in an experiment, it predicts the statistics that we would expect classically, okay? Because quantum mechanics, it's all about predicting the statistics of experiments, of observing observables and seeing what is the value that we get in the probability distributions that appear and so on. So then, essentially, what I was trying to convince you of is that coherent states are precisely the quantum state that predicts the statistics expected classically in experiments, okay? And we ended the class by showing that the first part, which is the fact that in quantum mechanics we have undefined trajectories, while in classical physics we have well-defined trajectories. we can recover it with coherent states in the following way. So imagine that you start with a coherent state alpha, and now you apply the evolution operator of the harmonic oscillator. Then I show you that in the Schrodinger picture, for example, the state, okay, at any given time, it's still a coherent state, but with an amplitude whose phase evolves linearly with time, okay, changes linearly with time. And this is precisely what we saw for the classical complex amplitude of the harmonic oscillator. And in particular, we discussed how, because of this property, the expectation value of the annihilation operator, or similarly of positional momentum, describes a circle in phase space, which is precisely the circle that is described, or the circular trajectory that is described classically, as we saw a few lectures ago. And moreover, because the uncertainty is equal to 1 for in all directions of phase space around the state, okay, then we saw that the signal to noise ratio that you would measure in an experiment, if you ask yourself what is the average of X and P and what are the fluctuations of X and P that I am observing, the signal to noise ratio goes to infinity when the coherent state gets larger and larger amplitude. So this means that for all practical purposes, we recover the classical trajectories with negligible noise, because at some point, this quantum noise, okay, this quantum noise delta X, it will be smaller than the noise that we have in the experiment, because laboratories have some noise, they are not perfect, right? So then essentially, we saw that for all practical purposes, classical trajectories are recovered with coherent states. And this is a super important point in quantum mechanics in general, but certainly in quantum optics and coherent state physics. Okay, so then with this, we can then move on to lecture 5. And let's start with the second part of the connection between classical and quantum physics, which is how we recover a continuous energy spectrum from this energy quantized spectrum that quantum physics predicts for the harmonic oscillator. And the idea is actually very, very simple. The idea goes as follows. So let me just write it here, continuous energy. So the idea is just as simple as the following. So let's consider the energy difference between two consecutive energies of the quantum energy spectrum, okay? We know that this is equal to what? This is equal to h bar omega, right? So this is what we saw for the spectrum of the harmonic oscillator. So then in an experiment, let's say the quantization that you observe is h bar omega. But let's compare that with the mean, not the mean, sorry, with the energy that you can observe experimentally, which are the ENs themselves. And as we said, this energy is just h bar omega times n plus 1/2 that we will not care much about. But what's important is that you see that if we take the limit of n very large, okay, so if n goes to infinity or n becomes very, very large, then we see that the quantization that you observe in relation to the energy that you are observing goes towards 0, okay? So this is very important because it is telling you that if you, in the experiment, you can only measure energies that are very large, okay, then you will never be able to see the quantization because let's say that your error bar in the experiment, again, the noise of your experiment, the error bar that you observe which maybe is a few percent of this, so maybe 0.01% of the energy or whatever, is much larger than the actual energy difference, okay, between the quantized energy levels. So, and this is precisely what happens for coherent states. So let me phrase this exactly. So for all practical purposes, again, we recover a continuous energy spectrum if we have a zero probability, okay, for n's, okay, that are not very large. So let's say for n's which are not much larger than 1. So if we are sure that we cannot measure small energies in the experiment, then we are sure that we will never observe quantization because the energy difference between the quantized levels is much smaller than the energy itself. And this is precisely what happens with coherent states. This is, so Pn equals 0 for n much larger than 1 as in coherent states. Of course, with alpha much larger than 1. Okay, let me better write it in this way. Coherent states alpha with alpha much larger than 1, for which we have seen that the uncertainty in the quanta related in relation, so in the quanta or in the energy, because it's the same, energy is proportional to the number of quanta, in relation to the average of quanta, this is alpha divided alpha square, which goes to 0 when alpha square, or when alpha is much larger than 1, okay? So then coherent states have this precise property that we are looking for, that we will, for example, the probability of observing the vacuum state when you are in a coherent state of very large amplitude, that's essentially 0, okay? You will always observe only outcomes of the energy that correspond to quanta around alpha square, okay? Never are close to 0. So then you see that coherent states, indeed, they allow you to recover continuous energy for all practical purposes, and they allow you to recover well-defined trajectories for all practical purposes in experiments, provided that they have a large amplitude. And then these are essentially the link between classical and quantum physics. So we might use during the course this link quite a bit. And in general, it's something that is very important for you to know if you have a model, a bosonic model. So a model with bosonic operators, annihilation operators, and creation operators. And you assume that the state of your model is a coherent state, okay? Then you will recover your classical theory. And this is very important also in quantum field theory, for example, and in many branches of quantum physics. Okay, so let's then, if there are no questions here, let's then move on to the next part of the, it's the almost last section of the chapter. We have 2 more states that we are going to study. And the first type of states that we are going to study are these squeezed states. So in order to introduce these squeezed states, let me explain you first something interesting, which is that the main interest of this type of states appears in the following context. It's an application of the electromagnetic field, or in general of harmonic oscillators, which is sensing or the encoding of information. Okay, and I give you one very modern and very interesting example, which is LIGO. So I'm sure you are all familiar with what LIGO is, but essentially LIGO is this gravitational wave interferometer, in which what we do is that we have an optical interferometer in which we have light circulating inside, and somehow, by a very clever way, we manage to encode the gravitational wave, so the information of the gravitational wave, the effect of the gravitational wave, into modulations of the amplitude or the phase of the harmonic oscillator, or in our case, light, the electromagnetic field. So let me bring back 1 second this picture where we have the amplitude and phase of the oscillator. So what I mean is exactly the following. So as we just discussed a little bit, so we have here the coherent state, okay? We have the harmonic oscillator essentially centered in this region of phase space. And what we do for sensing and for encoding information is that we introduce, so if the oscillator is here, what we do is that the signal that we want to sense or the information that we want to encode, we essentially encode it as fluctuations, okay? Fluctuations of this, of the mean amplitude, for example. Also with the phase, it doesn't matter, amplitude, phase, or anything else. So of our oscillator. So essentially we will have an oscillator that instead of being centered at that point, will be oscillating, okay? Will be modulated between the two values that, for example, could be maybe one value is here, another value is here, and then it's doing something like this, okay? Then whenever we observe that it's doing something like that, we get information about the signal that we are encoding. However, from the plot, you see already something very interesting, which is that if the signal that we want to encode, it's so tiny, okay, as gravitational waves are. So it's so small that the modulation happens within the uncertainty of our state, then we cannot distinguish it, okay? We cannot see it, we cannot resolve it. So the resolution of our experiment, of the resolution or the sensitivity that our experiment has to external signals, it's set by this uncertainty of the quadratures. And this is why we call this uncertainty of quadratures. So the fact that the uncertainty of any quadrature in any direction phi is equal to 1, we say that this sets a limit to sensing or information encoding, and we call this limit quantum shot noise. Okay, so essentially the uncertainty principle applied to states that are rotationally symmetric, or just the uncertainty of the quadratures in a coherent state, sets a limit to how precise we can do measurements or we can do sensing of signals such as gravitational waves. And then now the question that some people put forward in the 80s was the following, was, okay, does this mean that quantum mechanics sets this limit on sensing and we cannot go beyond it? So the answer is a little bit more subtle than you might think. The answer is no, okay? We can actually beat this quantum shot noise limit, and we can do it using something that are called squeezed states. So let me introduce you what are squeezed states, and then you will see right away that this is the case. So In particular, squeezed states appear from the following idea. It's a very simple one. So we were saying that so we have the fluctuations, for example, of amplitude. Remember that this phi refers to the phase of the harmonic oscillator in the coherent state or in the Gaussian state in general. So we have the fact that the uncertainty in position and the uncertainty in momentum has to be larger or equal than 1 when we multiply them, okay? But there is nothing, okay, there is nothing that prevents that we can take one of them, for example, the amplitude, we can make it smaller than 1, okay? Why not? Of course, if we make it smaller than 1, quantum mechanics forces you to have an uncertainty that is larger than 1 for the momentum 1, okay, for the P1. But at least we have managed to make the uncertainty of one of them smaller. And in particular, let me show you what this means with a picture. So essentially, this means, let me take the right one. Yes, so this is the one. So let me make some space. So can you see the figure properly? Maybe I make it a bit bigger. Okay. So in particular, what we see here is that we have squeezed the circle of the coherent state. We have squeezed it in the direction of the amplitude, okay, of the intensity. And therefore, we have stretched it or anti-squeezed it, we will call it, in the direction of the phase, okay? So this is what we call amplitude squeezed state. And of course, what happens now is that if the signal that we were encoding now has this amplitude, so this modulation amplitude, so now our oscillator, when coupled to the signal, will be modulated going back and forth between these 2 points. Now you see that while before it was masked by quantum uncertainty, now it's not anymore, okay? So we have been able to bring the noise in this direction, so in the direction of the modulation, below the signal. And actually, this is something that nowadays is used already in gravitational wave detectors. The sensitivity of gravitational wave detectors has been improved in the new generation thanks to using this kind of light with squeezing, okay? So let me bring back a little bit and let me bring this here. So then in general, we will say that any state for which we find that the uncertainty of some quadrature in some direction, it doesn't matter which direction, for some direction, is smaller than 1, when we have this, then we will say that we are in a squeezed state. Okay? And the notation that we will use is that in these conditions, then the quadratures x phi and p phi, we will call them the squeezed quadrature and the anti-squeezed quadrature. And it's very important to understand that you are only, so these squeezed states will be useful only when the squeeze quadrature is precisely the quadrature where you encode the modulation, okay? The signal that you want to send, or the information that you want to send. And if by some, by some error, you actually encode the information in some direction like this one, perhaps you are even making it worse by doing squeezing, because in the direction that is not the one that is squeezed, okay, in particular in the orthogonal to it, actually you are putting more noise. So you are reducing your sensitivity, okay? So then it's important that, that you always put the squeezing in the right direction that you want. And so together with this amplitude squeezed state, let me just show you a phase squeezed state. I guess that you can understand the idea, but let me show you explicitly. So this thing in here is a state in which now what we have is that the quadrature, that is the phase quadrature, is the one that has fluctuations or uncertainty smaller than the one of a coherent state. So, and then we call it phase squeezed state. Okay, so in particular, just looking here, remember that essentially the phase uncertainty is related to this kind of angle that is subtended by this uncertainty blur in here. And we see that in this case, this thing is stretched in the direction of the phase, which means that while in here this delta phi has all this, let's say, angle, in here the delta phi is much smaller, okay? So this is why we call it phase squeezed. So these are concepts that are quite important to understanding quantum optics. And of course, if you want to encode a signal in this squeezed state, what you need to do is encode the signal in the direction of the phase, not in the direction of the amplitude, okay? So very good. So this is the general definition of squeezed states. Whenever you find in your life a state that has fluctuations in one quadrature that are below the one of vacuum or the one of a coherent state, then you can call that squeezed state. But now we are going to discuss a very special type of squeezed states that are the simplest ones. And are actually the ones that we generate in the laboratory, which are minimum uncertainty squeezed states. So let me start by defining what I mean by minimum uncertainty. So minimum uncertainty states.
Is the squeeze always a Gaussian?
Yeah.
Is the squeeze state always Gaussian?
No, that's very important. That's a very good question. So in principle, whenever you have this condition, okay, you can call it a squeezed state, okay? And you can use it for measuring beyond the shot noise limit in an experiment and so on, okay?
Okay.
So that's very important. But the squeezed states that we are going to work with and the squeezed states that are usually generated in the lab, they are mostly Gaussian of this type, okay? But very, very good question, thanks. So minimum uncertainty states, what are they? So these are states for which the fluctuations in a canonical pair, so positional momentum in any direction, are equal to 1. And you can say for all 5, because actually what we can say is that the determinant of the covariance matrix is equal to 1. Remember that the determinant of B is the quantities or the determinant of the covariance matrix. And again, it doesn't matter if it's squeezed, if it's Gaussian states or not, you can define a covariance matrix for any state. So the determinant of B is the object the general object that encodes all the uncertainty principle, and whenever it's equal to 1, we say that we have the minimal possible noise. So we are in the family of states that have the minimal possible noise in quantum mechanics. So any other state that is not like this necessarily has more noise because of the uncertainty principle, because the determinant will be larger than 1. So, and I give you just a couple of examples, positive and negative examples. So first of all, coherent states. So coherent states are minimum uncertainty states, and this we know because we have already seen many times that the quadrature fluctuations in a coherent state are equal to 1 for all directions, and therefore the product is equal to 1. But what about Fox states? So Fox states, let's say a generic Fox state n, you can check by yourself, so it's a very easy calculation, that for any quadrature, the uncertainty is equal to 1 plus 2n, okay? This is for all phi. And then this automatically means that they are not minimum uncertainty states, because if you take a pair delta x and delta p, and you multiply the uncertainties, the multiplication is 1 plus 2n squared, which is larger than 1, not equal to 1. So, of course, there is one state, one Fox state that satisfies that it's a minimum uncertainty state, and that's the vacuum state. But that's not a surprise, because coherent state with 0 amplitude is also the vacuum state. So any Fox state with n larger than 0 is not a minimum uncertainty state. This doesn't mean it cannot be squeezed, okay? We can start from a Fox state and then do some operation to squeeze it. That's not a problem, but it will just not be a minimum uncertainty squeezed state. Okay, so then if this is clear, let me then explain you how to actually generate squeezing. And this is very simple because we just need the simplest generalization of the displacement operator, but within still the Gaussian world. And this is something called the squeezing operator. So the squeezing operator is a Gaussian unitary. I remind you that Gaussian unitary means that it's a unitary transformation, or comes from a Hamiltonian, that is at most quadratic in annihilation and creation operators or positional momentum, and it maps Gaussian states into Gaussian states. So we will parameterize it with some parameter set, just like the displacement is parameterized with another parameter alpha. And this is just very similar to the displacement. So is set star A minus set A dagger, but with one important difference, that now instead of A and A dagger, we have A square and A dagger square, okay? So remember that the displacement operator was had exponent that was linear in annihilation and creation operators. That was the simplest Gaussian unitary, or while the squeezing operator has quadratic dependence on annihilation and creation operators, and therefore is not the simplest one, but let's say it's still a relatively simple one. And just for convenience, we divide by 2, okay? So the parameter of the transformation is set divided by 2, and in the coherent or in the displacement operator, it was just alpha. And this set, it's very important, this set is a complex parameter, just like in the displacement operator, and we will write it in amplitude and phase, or magnitude and phase, in this way, okay? So R is the magnitude of the squeezing parameter, and theta is the phase of the squeezing parameter. Okay, so let's then analyze the type of states that this type of unitary operation creates. And for this, the first thing that we always do, like with the displacement operator, is we see how this transformation transforms the quadratures, or in this case, we can do it with the annihilation operator. So in particular, what we ask first is, okay, if I apply the evolution associated to this operator, so I just apply the unitary transformation in a Heisenberg picture-like calculation, then I let you do it yourself because this is very simple. It's in the notes, so you can check it, but using the Baker-Campbell-Hausdorff formula that we have used already a few times, you can check that this is easily rewritten as A times the hyperbolic cosine of R minus then some phase, and then a dagger, the hyperbolic sign. Okay? So I let you copy it. I think I will need a bit more space. So let me make this expression a bit smaller. Okay. So as I say, this is something that you can check yourself, and this automatically implies. So it implies that if I apply this transformation on the quadratures, and in particular, the simplest one that you can check is the quadratures that go in the direction θ/2. So again, you have all this in the notes, so go through it carefully. But what I am saying is build the quadratures that are through an angle θ/2, not the real positional momentum. And then these quadratures get transformed with a very simple transformation, which is diagonal and looks like this. Okay. And look how simple this is. This is why I wrote it first in this rotated frame, θ/2, because now what this is saying is that the position in this θ/2 frame, it's squeezed while the momentum is stretched, okay? Because this is exponential of minus a positive number, and this is exponential of plus a positive number, okay? So this is precisely the type of operation that we are kind of looking for, right? We want to stretch in one direction and squeeze in the other. So in some contexts, this is sometimes called a dilation operation or something like this. And this type of operations are also very important in many other contexts of quantum field theory, not only for this kind of application. So we will call this matrix here Q, okay? So this diagonal matrix with a dilation, we will call it Q. And of course, we have already defined, or we have already seen that the rotated set of quadratures, we can find it just by taking the original positional momentum X and P and applying a rotation onto it, in this case, a rotation of θ/2, okay? Then this automatically implies that in the nomenclature that we were using for Gaussian operations, maybe because this is a while back, let me just remind you of it. So let me go to the definition of Gaussian operations and Gaussian states. Let me see where this is. It's here. So I remind you very quickly that we were saying that if we have an operation that it's quadratic in the quadratures, so a unitary transformation quadratic in the quadratures, this connects Gaussian states, and in particular, it defines a linear transformation that has some kind of matrix S and some vector A. So all the information about the unitary, about the quadratic unitary or Gaussian unitary, is encoded into these two things: the matrix S and the displacement or the vector A. So then we have to find for our Gaussian unitary. So for this Gaussian unitary, we have to find what are these A and S. And it's very simple to see that for our Gaussian unitary, what we have in this case, it's just that A is equal to 0. This you see automatically because you see that there is no displacement of A. So A, it's still proportional to A in A dagger, but it doesn't have something constant added to it, and the same for the quadrature. And now S is found in the following way. So S refers to the transformation that we are applying onto X and P, right? So we simply take this expression here and reminding that our, so the quadratures of an angle θ/2 are just this rotation in here. We can also put it in here. And what we get is an expression like this. So let me write it down. So I'm sure that you see what I am doing. So what I am saying is that for the normal quadrature, so not rotated, what we get is an expression that looks like this. This is R θ/2 Q of R and sorry, this is transpose and then θ/2 and then the quadratures. Okay, so you see that this thing in here is precisely the linear transformation matrix on R. Okay, so let me just make it small in here. Oops. So I keep it here but small. And then what I am saying is that this linear transformation S of Z, it's just a rotation onto this dilation matrix. Okay. So this is essentially the transformation, the linear transformation defined by the squeezing operation. And then it has a very, very specific meaning. What we are doing is we are making a dilation, but rotated by an angle θ/2. So which means that we are squeezing and anti-squeezing in the direction defined by the phase of Z/2. And so let's use this. So let's put to use. So this is just the unitary itself. You can apply the unitary to any state you want. In particular, if you apply this unitary transformation onto Foxtails, you might be able, if R is strong enough, so if the exponential of minus R is much larger than 1 plus 2n, then you are able to create a squeezed state that will be non-Gaussian because Foxtails are not Gaussian. But if you apply it to a Gaussian state, and in particular, we are going to apply it to vacuum and define something called the squeezed vacuum state. So the squeezed vacuum state defined by some parameter, squeezing parameter set, is just the squeezing operation acting on vacuum, just like coherent states correspond to the displacement operation acting on vacuum. And as we have seen, this state is a Gaussian state. with a displacement that it's 0. Why is it 0? Because the vacuum state is centered in the origin of phase space, so it has 0 displacement. And we have already seen that the squeezing transformation doesn't add any displacement. So A is equal to 0. And on the other hand, the covariance matrix of this squeezed vacuum state is just equal to, as we have seen in the expression that I have shown before, it will be just the linear transformation of the covariance matrix of vacuum. But what is the covariance matrix of vacuum? Anyone remembers? Go ahead and say it if that's the case. So just try to think, what is the property that defines vacuum? It is rotationally invariant. And what is the uncertainty in any direction of phase space? So how much is the uncertainty of vacuum? So the uncertainty of the quadratures in the vacuum state. We have been using it all the time. So I'm sure some of you know, yes. Don't be shy, please. We have already 5 lectures, so we are basically good friends. So yes, so this is the identity. And the S transformation, we see that is just the Q matrix, which is diagonal. And then the rotation. And therefore, what we get is something very simple. We get the following. So this and then this. So what we get is essentially that the covariance matrix itself is equal to this dilation matrix, but now of 2R, not 1R, but 2R, and rotated. So this expression is really nice because it automatically shows us a couple of things. The first one, it's this one I'm going to show. So it tells us that this Gaussian state is a Gaussian state that is centered at 0. Okay, but along the directions defined by the angle θ/2, it's squeezed in the x direction and anti-squeezed in the p direction. Okay, so we see here that in the p direction, the uncertainty is much larger than 1, is exponential of 2r, sorry. The variance is exponential of 2r, so the uncertainty is exponential of r. And in here, the uncertainty in the direction of x will be exponential of minus r. Okay? But of course, by construction, you can also check very easily that this covariance matrix, so the covariance matrix of this squeezed coherent state is equal to 1. So it's a minimum uncertainty state. And this is very simple because I remind you that this matrix is just exponential of 2r minus 2r exponential of 2r. And therefore the determinant of V is just the determinant of r times the determinant of q, which is 1, and the determinant of r. And of course, the determinant of a rotation is 1, as you know very well. So then we get determinant equal 1. So you see what is a squeezed vacuum state is just literally taking the vacuum state, which is a circle in here, and then applying squeezing in one direction θ/2 and anti-squeezing or stretching in the direction p of θ/2. Okay, then once we have a squeezed vacuum state, it's actually very easy to generate amplitude and phase squeezed states. And this is what I am showing here. So in particular, once we have our squeezed vacuum state, if we apply a displacement operation, okay, we have already seen the displacement in the direction of P, then we get a phase squeezed state. So you see that this state in here has a phase fluctuation. So the fluctuations in this direction are smaller than the ones of vacuum. That would be maybe something like this, okay? And if we apply the displacement in the direction of the x, okay, the x in the θ/2 direction, then what we get instead is an amplitude squeezed state, because now the fluctuations are small in this direction, which is the amplitude direction, compared to the fluctuations that would be in the vacuum state, for example, these ones, okay? So we see that at the end of the day, combining Gaussian operations, we can create the type of Gaussian states that we want, in particular, in this case, squeezed states. And this is precisely what's done in the gravitational wave detector of LIGO, for example. So you put laser light inside, and maybe we will see in the course, but it's good that you already keep it in mind that the laser basically is equivalent to a coherent state. It's a bit more subtle than that, but you can just think that the light of a laser is in a coherent state. But then you also put in there some, in the gravitational wave detector, I mean, you put a squeezed vacuum light, okay, that we can generate in some way that we will learn in this course. Not in the next chapter, but in the next one. So we mix these two. So we mix laser light with squeezed vacuum light, and then we create some type of squeezed state that it's amplitude squeezed or phase squeezed, whatever we want, okay? So then let me say one last thing about squeezed states, which is related to the Fock state representation. So the Fock state representation of the squeezed vacuum state, I will write it. I will not prove it here, but you have it in the notes as well. It requires a couple of interesting but technical expressions. So it looks like this. It looks like, so let me first write it and then we discuss it. So the amplitude in the, so the probability amplitude of being in the Fock states look like this funny expression here. And what's very important is this final thing in here. So this thing in here. So only even Fock states contribute to the representation of the squeezed vacuum state. But I hope this is not a surprise, because I remind you what is the squeezing operator. The squeezing operator depends on A dagger square and A square, right? So you can only generate excitations by pairs. So if you start from 0, which is the vacuum state, and then you start applying powers, okay, powers of this exponent, you will always create excitations pair by pair. So you can only have even number of quanta. So this is the smoking gun for squeezing, actually. Whenever you have a state, or is one of the smoking guns, whenever you have a squeezed a state in the lab where you see that only even states contribute, then you can start thinking about the fact that maybe you have a squeezed state. There are other quantum states that have this property, but this is one of the defining properties of squeezed states. And then the other important thing about squeezed states or squeezed vacuum state is that it's very simple. So I recommend you to try it as well to calculate. Just from this transformation here, this is the easiest to work with. So you know how the A and A dagger operators are transformed through the unitary squeezing operation. And then it's very simple to check that in a squeezed state, the expectation value, so let me be more explicit. So the expectation value of the number operator, it's equal to the hyperbolic sine square of R. So it's always important to check limits. So when R goes to 0, which means that you are not applying squeezing, then what is the value of the hyperbolic sine is 0. So we get 0 number or expectation value of the number, which corresponds to the vacuum state. So that looks good. On the other hand, you can calculate the variance. So the variance of n in the squeezed state, and you can see that this is equal to an expression that looks like this: a hyperbolic sine of R to the 4th plus hyperbolic sine squared. Okay. So, oops, this should be a hyperbolic sine. So again, you can take the limit, and when you put R equals 0, all this becomes 0. So the variance of n is 0, and that's precisely what happens in the vacuum state, because the vacuum state is an eigenstate of the number operator. So this automatically means something very interesting, which is that if now you evaluate the fluctuations in quanta, the fluctuations in the number of quanta, compared, so the uncertainty of the number of quanta compared to the average of the number of quanta, then in this case, when the number of quanta goes to infinity, this goes to 1, not to 0, like what happened for coherent states. So this means that this distribution of quanta is very different from the Poisson distribution. Okay? And this is very important because this tells you that squeezed states and coherent states have very, very different properties, okay? And in particular, in this case, the signal to noise ratio that you would observe in experiments related to this kind of quantities, it doesn't go to classical, let's say. So this is very interesting. So this is one of the first hints that maybe this type of states, even if they are Gaussian, which means that the Wigner function is positive and so on, they still have some quantum interest, you know, in quantum applications. And in fact, I don't think that we will see this in the course, but maybe I will, maybe some of you will want to do it as a project or something like that. But it's very interesting that actually if you take squeezed states and you pass them through a beam splitter, so beam splitter means just something that is partially transmitting and partially reflective. So part of the beam goes through it and part of the beam is reflected. Then these reflected and transmitted beams are entangled, okay? So this is super interesting because this is telling you that even if the Wigner function is very simple and everything is positive and everything looks classical, at the end of the day, with something as simple as putting a beam splitter on them, you can generate something that is really, really quantum, which is an entangled state in which you have all these non-local effects of quantum mechanics and so on that you might have heard about, like Bell inequalities and so on. So, but this is just something that if you are interested in, I wanted to mention, and then you can study a bit more in detail. Okay, so these are essentially all the interesting features of squeezed states that I want to mention. And then we are now going to move to the last type of states that we are going to study in this chapter, which are thermal states. So if there are no questions about squeezed states, then we can move on to thermal states. We will start with something very general that is not related only to the harmonic oscillator, but really to completely general thermal states. And I think that's very useful for absolutely everyone. And then we will particularize it to the harmonic oscillator and the electromagnetic field. So let me introduce thermal states. What do I mean by a thermal state is the following. So we already saw something that we call the maximally mixed state. Which I remind you that it was the state that had the maximum possible mixedness, in the sense that it provides a minimum amount of information about predictions for measurements of observables. And we saw that this maximally mixed state is just equal to the identity, so the identity operator, and normalized to D. But this meant that this is well defined only for finite dimension. So when the dimension of the Hilbert space D, it's finite. Because when D goes towards infinity, okay, first of all, it has a weird normalization. Okay, so the normalization is very weird. So we are dividing the identity by an infinity. But on top of that, and this is the kind of the smoking gun for why this state doesn't work for infinite dimension, if we calculate for example, for the harmonic oscillator, the number of quanta, which is related to the energy of the oscillator in this state, so this is the identity, right? So this is the identity. So what we get is just something like this. We will get the sum from n equals 0 to infinity of n. So that comes from the operator, that's just the trace. That's just the trace of the operator n, okay, the number operator, divided by the dimension d. But the dimension d, I can write it like this, 0 to infinity of 1. So I sum 1 an infinite number of times. And this goes towards infinity. Okay. So as n goes to infinity, this is infinity because we have put the dimension d already infinity. So then this is telling you that this state, so this maximally mixed state in infinite dimension, has infinite energy. Infinite energy, which means that it's not physical. So it's unphysical. Okay, so if you want to generate a maximally mixed state of infinite dimension in this kind of definition, you need an infinite amount of energy, and therefore it's not possible to do that. So in other words, maximization of the entropy so remember that we find the maximally mixed state by maximizing the quantity that gives you the mixedness of the state, which is the entropy, only makes sense imposing some energy constraint. Okay, and in particular, energy constraint means that we will just ask the expectation value of the energy, so of the Hamiltonian, so the average energy, to be equal to something that we have available in the lab. For example, some average energy that we have fixed. Okay, so then what we are going to find is the state, rho, that maximizes the entropy, so it's as mixed as it can be for a given value of the available energy or available mean energy. So we will actually prove what is this state. We will do it later, but now I just want to give it to you and then we discuss some physics of it. And this state that maximizes the entropy for a given value of the mean energy, this is called thermal state. You will see why in a second. And it's given by this expression here. So it's just the exponential of minus some factor beta that I will show you in a second what it is, times the Hamiltonian. So essentially the exponential of minus the Hamiltonian. And of course, because the state has to be normalized, this is divided by the trace of that exponential, which is not 1 in general, and therefore to normalize the mixed state, we have to divide by that trace. Okay. Now, what is this beta parameter? This beta parameter, you find it just from the constraint. So in particular, we have the constraint that the mean energy is equal to the expectation value of the energy. So I remind you, the expectation value of the energy, the trace of Hamiltonian times state. So this means that this expectation value of the energy is just equal to the trace of Hamiltonian times exponential of minus beta Hamiltonian, and then divided by the trace of the exponential. Now this expression I can rewrite in a much nicer way, which is the derivative of beta of the logarithm of that trace. And now I will do something that we will use quite a lot, that is that I define the eigenstates of the Hamiltonian. So this is for a completely general Hamiltonian, it doesn't matter. So we have a Hamiltonian that has eigenstates. Here I am assuming that the eigenstates form a discrete set, but it would work also for a Hamiltonian with a continuous part in the spectrum. And therefore, when we use the basis of the Hamiltonian to evaluate the trace, because this is a function of the Hamiltonian, what we get is just something like this, minus derivative of beta of the logarithm. And now what we get here is something that might look familiar for all of you. So I don't know if you have studied a lot of statistical physics. So have you or not? Because I forgot to ask. So have you studied a course on statistical physics?
Yeah, for one semester.
Okay, but then for sure they have told you that this expression here, which is just the sum of the exponentials of minus beta and energy, that's called the partition function. Have you heard about it? Hopefully, yes. I mean, we will not need it too much. It's just that it's nice that you see how naturally the world of statistical physics is connected to the world of harmonic oscillators and the world of entropy and mixedness and so on, just by trying to find the state that maximizes the entropy and so on for a given value of the energy, of the mean energy. So, but essentially what I am trying to say in here is that if we try to maximize the entropy with an energy constraint, then what we get is a state that is this state here, the exponential of minus beta h divided this trace, which is a partition function, where this parameter beta is found from the energy constraint just by solving this expression in here. So this is an expression that depends on beta, okay? So beta as a function of the mean energy is implicit in this expression. And for the harmonic oscillator, we will see in particular what are the relations and so on. But then also what's important, so as I was saying, we call this thermal state. And why do we call it thermal state? Because for now, I should call it something like maximally mixed state subject to a constraint or something like that. The reason why we call it thermal state is the following. So what happens if I ask you what is the probability of obtaining in an experiment, when you measure the energy, obtaining eigenenergy En? So, of course, you know from what we have been discussing here that this will be given just by the expectation value of the state in the corresponding eigenvector of the Hamiltonian. But since this is an eigenvector of the Hamiltonian and the state depends only on the Hamiltonian, so this is just directly equal to the exponential of minus beta energy n divided by some normalization, which is the sum of all the possible exponentials. And again, if you have studied statistical physics, this is exactly the probability distribution expected for the energies when the system is at equilibrium at some temperature given by this beta parameter. So in particular, so let me write it down. This is what is expected for a system at thermal equilibrium with temperature 1 divided by the Boltzmann constant times beta, okay? So essentially, you can either see this state as the state that maximizes the entropy subject to an energy constraint, or as the state of the system when it is at thermal equilibrium at temperature T, 1 over beta, okay? And so remind me that I still owe you the proof that this is the actual state that maximizes the entropy, but just trust me on this for now. And then let's discuss a bit of the physics. So we have done already a bit of the physics in here. This is completely generic, but let's do it now for the harmonic oscillator. So what does this mean for the harmonic oscillator? So for the harmonic oscillator, so just check in here for 1 second, and the only important thing, or the most important thing that we have talked about in here for calculations, it's the energy spectrum, En. So for the harmonic oscillator, the energy spectrum is given, as we have written already many times, by h bar omega, and then n plus 1/2, and here n runs from 0 to infinity, okay? So then the most important object that one has to evaluate all the time in this context is the partition function. So the partition function that we have seen, this is equal to the exponential of minus beta Hamiltonian, so the trace of the exponential of minus beta Hamiltonian. And if we use the Hamiltonian eigenbasis for the trace, we get a very simple expression because this is minus beta h bar omega over 2. This is the exponential factor that comes from this 1/2 in the spectrum. And then we get the sum from n equals 0 to infinity of the part that depends on n. And the part that depends on n will have a minus beta h bar omega n. But let me write it as this exponential to the n. And then now, this sum is very simple to evaluate because this is something that you know as a geometric sum, which is very easy to prove that it's equal to the following. So imagine that I give you a sum of c to the m from 0 to capital M, and I tell you, this is very important, I tell you that c is smaller than 1. So if c is larger than 1, it doesn't work. So c, or the absolute value of c, if it's a complex number, it's smaller than 1. Then it's very simple to prove that this is equal to 1 minus c to the m plus 1 divided 1 minus c. So this is something that you have in the notes and probably you have already seen in some other lectures. So this is very simple to prove, at least when you know that the sum is convergent, okay? Of course, for finite m is always convergent, but when m goes to infinity, as we have in here, you have to be careful that it's convergent, but we know that this sum is convergent whenever c is smaller than 1. And then under those conditions, it's easy to prove this expression here, which means that at the end of the day, our partition function is just as simple as this quantity here. Okay. So this looks kind of nice, but let me then calculate. So the partition function, I remind you that is the first step in the calculation, for example, of the average energy. So the average energy that we are fixing, and then the relation between beta and the average energy. So then now what we need to find is what is the actual expression of this minus partial beta log of the partition function. And this is also very simple. So we just have to take derivatives and so on. So let me write it down carefully. So this is minus the derivative in beta of what? We have to take the logarithm of the partition function, but the partition function looks like this. So the logarithm can be written as the logarithm of the numerator minus the logarithm of the denominator. The numerator is an exponential, so we get finally only the exponent when we take the logarithm. So this is minus beta h bar omega over 2. And then we have minus the logarithm of the denominator, which is logarithm of 1 minus exponential minus beta h bar omega. Then if we take the derivative with respect to beta, then the first term is linear in beta, in beta. So then it gives us h bar omega over 2. And the second term is the logarithm that after taking the derivative carefully, you will find h bar omega divided e to the beta h bar omega minus 1. Okay. Let me move things a bit. I need more space. And I can make this smaller. Okay. So then now, you see that now we have a relation between beta and the energy, but in particular, this is something that you, I hope, are familiar with, Because if we define, instead of the average energy, we define the average excitation number or number of quanta. So we define it as the expectation value of the number operator in the thermal state. Then, of course, by definition, because the Hamiltonian is just h bar omega number operator plus 1/2, then the average energy is equal to h bar omega average excitation number plus 1/2. And when we use this expression, so instead of writing things in terms of the average energy, we do it in terms of the average excitation number or quanta number, which is the same for the harmonic oscillator. It's, for the harmonic oscillator, is the same talking about number of quanta or energy. Then we get the following relation, which, as I said, I hope that you have seen at least once in your life. This is called the Bose-Einstein distribution. Okay, and this is a super important distribution because it tells you the following information. If I tell you that I have a system at equilibrium, so a harmonic oscillator at equilibrium at some temperature beta or 1/beta, and the harmonic oscillator has a frequency omega or an energy h bar omega, okay? So then beta is the inverse of the thermal energy and h bar omega is the natural scale of the oscillator. This expression is simply telling you how many excitations you will find in that system that has an energy scale h bar omega for that thermal energy 1/beta, okay? And this distribution, therefore, it's very, very important in the world of bosonic physics. And then probably you know that there is an equivalent expression for fermions that it's similar to this one, but has a plus in here and so on and so forth. So this appears very naturally when we simply ask for what is the average excitation number in a thermal state, okay? So this is one thing I wanted to discuss. The next thing I want to discuss is the Fock state expansion of the thermal state. So the Fock state expansion. So now the thermal state, instead of parametrizing it with the mean energy, we can, as I said, parametrize it with the mean number of excitations, which for the harmonic oscillator is the same and is more convenient. So first of all, you see that the thermal state depends only on the Hamiltonian, right? And the Fock states are eigenstates of the Hamiltonian, which means that they are eigenstates of the thermal state, meaning that the thermal state is actually diagonal. Is diagonal in the Fock state basis. And in particular, you can write the probability of having n quanta, so Pn, for a given average energy or average excitation number n. You can write it in this easy to remember form, in which you just divide n to the n by 1 plus n to the 1 plus n, okay? So it's a very simple expression. So what's interesting about this is that, so first of all, is diagonal as the maximally mixed state for finite dimension, okay? So remember that the maximally mixed state for finite dimension is the identity The identity is just a diagonal of 1 over d. And the same happens with the thermal state. It's diagonal, but the distribution Pn is not flat. It's not 1 for each n, okay? However, this distribution here actually becomes flatter and flatter as n increases, okay? So in particular, what you can see very easily is that Pn is approximately equal to Pn plus 1, for example, when the available energy, so the mean number of excitations, is much larger than n. Okay, so if you are asking the question of how is the relative probability between being in vacuum and the first excited state when I have an average energy of 100 quanta, okay? Then what's happening is that probability distributions are almost the same, okay? Because they are exponentially close. And therefore, you see that initially the distribution is actually flat, okay? And you can only see that it's not flat when you go to very large excitation numbers, so n on the order of n, okay? So the quanta on the order of the average quanta, then you can start seeing how the probability distribution decays, okay? But when the energy is infinity, therefore all the probabilities are the same and we recover what we expect. Okay, so another way of saying it that you might have heard is that when the temperature goes to infinity, of course, there is a relation between the temperature being large and the energy, the available energy being large. So when the temperature goes to infinity, so when beta goes to 0, then you recover a flat distribution. So you recover the maximally mixed state, okay? And this is true for finite dimension as well, because what I showed you is completely general for any system. It doesn't matter which system. If you have a Hamiltonian, you can define the maximally mixed state for a finite energy, okay? And when the temperature goes to infinity, you get the maximally mixed state or the thermal state if the energy is finite, the available energy is finite. So I hope this is kind of interesting, especially if you have seen statistical physics already. And then what I want to show you now is that this thermal state is actually Gaussian. So let's do the proof that this state is Gaussian. How can we do this? It's actually very simple in this case. We simply use the criterion that we discussed based on coherent states that tells us that we just need to take the expectation value of the state in a coherent state with amplitude mu. And if we get the exponential of a quadratic form of nu, then we know that the state is Gaussian. So this means that we need to take the expectation value of minus beta Hamiltonian, but for the harmonic oscillator, the Hamiltonian is just h bar omega n times nu. Okay, and of course we have more constant factors that do not contribute anyways, like the 1/2, so the 1/2 of the Hamiltonian, or the normalization with the partition function of the thermal state. But all we need to prove is that this part of the expectation value is quadratic, is the exponential of a quadratic form of mu. Then this is very easy to prove because we can use the Foxtail representation of this exponential. And we get something very simple. It's just n equals 0 to infinity exponential of minus beta h bar omega n. So the eigenvalue of the number operator. And then in here, we get nu n n mu. But what is this? This is just the same as just saying absolute value of the overlap between a coherent state, a coherent state and a Fock state n. Okay. And we know what this is. So this overlap, we have seen it already because we know the Fock state representation of coherent states. This was just the Poisson distribution. So the complex form of it, because we have the expectation value, sorry, the overlap, not the overlap square. But when we put it in the overlap square, this is precisely the Poisson distribution. And what we get is something like this. So first of all, this exponential here doesn't depend on n, right? Which means that I can put it out of the sum. And now what we get is the sum from n equals 0 to infinity. And now looking here, we have the square of 1 over square root factorial. So this is 1 over n factorial. And now we have something. So we have mu to the n, and we have this exponential of minus beta h bar omega to the n as well. So this is just minus exponential of beta h bar omega mu to the n, sorry, square to the n. Okay. So we have essentially finished because you see that this sum in here, or this series here, is just the series for the exponential of this. So finally, we end up with an expression that looks a bit funny because it has exponentials in the exponent, but we don't care about that because what we find, minus beta h bar omega minus 1 to the nu square, what we find is an expression that looks like this. So we get the minus 1 from this exponential that is outside, and then we get this exponential of minus beta h bar omega in here. But we see that this is the exponential of a quadratic form. Okay. So this is a quadratic form in nu. So in general in nu, which actually means that rho thermal is Gaussian. Like I told you and like I wanted to prove. Okay? So I hope this was clear, but otherwise just try to do it by yourself as well. And of course, as usual, is in the notes in all sorts of detail. But the only important thing is that we prove that the thermal state is Gaussian. And once we know that the thermal state is Gaussian, then we can plot it in phase space and understand how it is. In particular, we can find very easily the moments, so the first and second order moments. So if I ask you what is the expectation value of A, I hope you will see very quickly that this is equal to 0. And the reason is very simple. So the expectation value of A is just the trace of rho thermal A. If we represent it in the Fock basis, this is just equal n0 to infinity of the probability distribution in the thermal state, and then n, A, n. But we know that A acting on n, that brings us to n minus 1. So then this state here, n is orthogonal to n. So therefore, this is equal to 0. And of course, the same happens with A square. If you do A square, which is the trace of rho thermal A square, This will be equal to the sum from 0 to infinity, weighted by the probability distribution in the Foxtails, and then a square n. But now, again, this state a square n is proportional to n minus 2, which means that this whole state is orthogonal to n. So this is 0. And finally, we can also check a dagger A, but a dagger A is actually the constraint. So a dagger A is the mean number of excitations. So that's by definition, the parameter n of the thermal state, the constraint that we have added. What is the mean energy of the thermal state? So this automatically means that the mean vector of the thermal state is 0, and the covariance matrix of the thermal state can be written in the following way. So it's proportional to the identity, just like the vacuum state, but with a variance that is not equal to 1. So the variance in vacuum is equal to 1. The variance in the thermal state is not equal to 1, but it's actually much larger by a factor 2n, okay, 2n plus 1. So this means that if we just plot the Wigner function, and then we get an intuitive idea of how the thermal state is in phase space, this is what we get. So if this is the Wigner function of the vacuum state, which is a circle, uncertainty circle around the origin of phase space, then the one of a thermal state, for example, for n equal 4, is just also a circle, but it's a circle that has much more noise, okay, by a factor square root of 5. Sorry, a factor 3 probably, no? Because it's 2 times 4. Yeah, so it's the square root of 9. So then it's by a factor 3, okay? So it's essentially similar to vacuum, but with a much larger noise, which is kind of what you would expect, because in an experiment, if I tell you that you have 0 temperature, that's ideal. It means that everything is quiet, nothing is moving. But what does it mean, temperature? What does it mean to have some temperature in statistical physics? What it means is that essentially, if you have particles, for example, your particles are actually moving around. They have some thermal energy, some thermal activation. And therefore, what you will have is that you are adding some noise because this energy is distributed randomly and the motion is random. You have noise onto what you would think that it's control, okay? So you might think that your harmonic oscillator is very quiet at equilibrium, but what's happening is that because it has some temperature, it's actually moving randomly, okay? But in a way that is actually much more noisy than just quantum fluctuations or vacuum fluctuations, okay? So this is essentially a thermal state. So it's this kind of Gaussian state. So it looks extremely simple in phase space, but look at how deep it is and how many interesting features it has related to statistical physics. So then now, I still owe you a proof. So I will do it now. I remind you that the proof I owe you is that we started this section saying that if you maximize the entropy subject to an energy constraint, then this is the solution, the thermal state. And again, this is completely general. It has nothing to do with a harmonic oscillator. It's just absolutely general for any system, any Hamiltonian, any dimension, whatever you want. So let's do the proof of this, because I think it's a very interesting proof for many reasons. So the proof goes as follows. So what we will use is something that you are familiar with, probably from math, but for sure from classical mechanics and from thermodynamics, which is Lagrange optimization. So what is Lagrange optimization? Is the following. We first build a functional that we will call the Lagrange Functional, in which we put the function that we want to optimize, which in this case, or maximize, which in this case is the entropy. And I remind you that the entropy is just given by this expression here. Okay, minus rho log rho with a trace. And we add the constraints with Lagrange multipliers. So I have a Lagrange multiplier lambda that contains the norm or the normalization constraint. So this is the normalization constraint, this thing here. And we have another constraint that we have imposed, that is the mean energy, right? So the mean energy has to be equal to the trace of H rho. So this is the, oops, this is the energy constraint. Okay, so, well, when I say that this is the normalization constraint, of course, what I mean is this equal to 0 is the normalization constraint, and this equal to 0 is the energy constraint. And then Lagrange optimization, what you do is simply you make a variation of the Lagrange functional, which now it doesn't depend only on the state rho, which is the variable that we want to optimize, but also on the Lagrange multipliers. So let me just write it here. So it depends also on lambda and beta, which are Lagrange multipliers. And then what we ask is that this Lagrange functional, when we make a variation of the things it depends on, so the state, the lambda and beta, it's equal to 0. So that variation, it's equal to 0. So in particular, let me write it down. So what we ask, so is that I will not write the dependence on lambda and beta all the time. We ask that the Lagrange multiplier, for example, sorry, the Lagrange functional, the variation with respect to the state, which is defined as the Lagrange functional when you do a variation of the state, delta rho, minus the Lagrange functional when you don't do the variation. This is equal. And now the whole proof relies only on 2 results. The first result is this one, that the variation of the logarithm is equal to the inverse of the variable times the variation of the variable. So this is something that in the world of derivation, you know, so the derivative of the logarithm is just the derivative of what's inside the logarithm divided what's inside the logarithm. So that's something that you are familiar with. The only reason why I write it here in this way is that this is an operator. So I know that for some people it might be a bit weird to take the variation of an operator and do operators obey the usual relations of variables and so on. Generally, no. But in this case, this is completely true. And most important, rho and the variation of rho, you can assume that they commute. And the reason why you can assume that they commute is very simple. Is the following. So first of all, we are looking for a state that it's stationary, right? So we don't have time dependence of anything. We are just looking for one specific state that is the one that maximizes the entropy, okay? And that's one state. It's not a family of states that depend on a parameter called time, okay? It's a single one. Therefore, this automatically implies by the von Neumann equation that the Hamiltonian commutes with the state, or the state commutes with the Hamiltonian, okay? And then this automatically means that the state is diagonal in the basis of the Hamiltonian, okay? And therefore, we know that. So we know that the state that maximizes the entropy is diagonal in the basis of the Hamiltonian. And this automatically means that we can choose variations which are also diagonal in the basis of the Hamiltonian, because we don't need to check variations that are not diagonal. We know that the state that maximizes the entropy will be diagonal. And therefore, if rho and the variations are diagonal in the same basis, they commute, okay? So it's just as simple as this. So then using these expressions here, then it's very easy to find that this expression here is equal to minus the trace. And then let's start writing things. So what happens when you take the variation of the first term in here? So look in here, we have rho log rho. So we have to take the variation of the first without doing a variation of the second, and the variation of the second without making a variation of the first, okay? So this will give us exactly a variation of delta, and then a 1. So if you want first a log of rho, and then a 1. Let me remove this. So I repeat. So if we just take the variation of the first times log, that's the first term, this. And if we take rho, the variation of the log, we have seen that the variation of the log is rho minus 1 delta rho. And then this rho minus 1 with rho cancels, and you get a 1 times delta rho, okay? On the other hand, the variation of rho, it's just the variation of rho. And here the variation of h times rho is just h, the variation of rho. And therefore, we get 2 more terms, which are also trivial, which are these ones here. Okay? And Lagrange optimization means that you are asking the variation. So you are asking for the variable that makes the variation equal to 0. So this is optimization. Then this automatically implies, as you see, if this is true for any variation delta rho, okay, it has to be equal for any variation delta rho, then this implies that this operator here has to be 0. And automatically, this implies that rho has to be equal. So log rho has to be equal. Log rho has to be equal to all this, which means that rho has to be equal to the exponential of minus lambda plus 1, exponential of minus beta h. And now lambda and beta can be found by making the variation with respect to lambda and beta and putting it to 0, but that's equivalent to just saying the constraint. So trace rho 1, trace of rho equal to 1, and trace of h rho equal to e. So in other words, so from the constraint of trace of rho equal to 1, we find exactly what we expect, that is that all this factor, so the exponential of minus lambda plus 1, all this factor is equal to the trace of rho, which is 1, and the trace of minus beta h in the denominator. Okay, and this so finishes the proof that the state that maximizes the entropy for an energy constraint is just exactly the thermal state that we have defined in here. Okay. So any question in here? If the derivation was a bit too fast or there are some points that you are not sure about, just go to the lecture notes, check the derivation carefully, do it yourself, and feel free to ask me anything that you need. But essentially, this is everything I want to say about thermal states. So if there are no questions, then I will just finish with some remarks about the quantized electromagnetic field. Remember that the whole chapter was about quantization of the electromagnetic field. It's just that we saw that the electromagnetic field is just a collection of harmonic oscillators, and therefore we focused on what is the quantum mechanics of a harmonic oscillator. But now let me come back and just finish the chapter by reminding you some things of the quantized electromagnetic field. So feel free to ask if there is any question, but otherwise let me just start with this part. So I remind you very quickly that the first thing that we did when we started the chapter was quantizing the electromagnetic field inside an optical cavity, okay? An optical cavity, we defined it in this way. So basically 2 mirrors which are perfectly reflecting and separated by a length L, by a distance L. And then some of the things that we found is that inside this optical cavity, not every frequency is allowed, but we have some mode frequencies. And these mode frequencies are frequencies, so let me call them omega m, or equivalently wave vectors k, which are a multiple, an integer multiple of pi c divided by L. And this m is any natural number. Okay? Now, associated to every frequency available in the system, we define a harmonic oscillator. And now that we know that in the harmonic oscillator, what we care about, or a description that is very useful, it's annihilation and creation operators. So we can define the modal or the mode annihilation operators. And what are these? So in terms of the positional momentum, which in the context of the electromagnetic field, the position was associated with the amplitude of the vector potential or the magnetic field, and the momentum was associated with the amplitude of the electric field, we can write it in this way. So this is omega m divided 2h bar, and then the amplitude q, so position, amplitude of the magnetic field, plus I over omega m, p, which is the amplitude of the electric field. And most importantly, we are doing quantum field theory because we are imposing canonical commutation relations with, in terms of annihilation and creation operators, look like this. A with a dagger, it's equal to 1 for the same mode and 0 for different modes. Okay? Now, how about the fields? So we have several important fields. First, the vector potential, which is now a quantum mechanical operator, A. And we saw that it can be written in terms of the annihilation operators in the following way. So first of all, it has some polarization that we chose as X. Then it has a sum over all the possible modes. And then in here, we get a like a normalization factor or an amplitude, h bar divided epsilon 0 L S omega m. And I remind you that this S in here is the surface of the section of the cavity, which we assume is finite, even if we are using kind of an infinite description. So it's large but finite. And then we have the annihilation operator associated to mode M and the spatial shape of the mode M, which is a sine. So it's a standing wave of the cavity, plus the harmonic, the Hermitian conjugate, okay? So this is for the vector potential. Then we have the same expression or similar expression for the electric field, which is the minus the time derivative of the vector potential. And this can be written in the following way. So this is Ex sum m equals 0 to infinity h bar epsilon 0 L S omega m a m in the same sign. And finally, we have the magnetic field. So this is also an operator, the electric field, and the magnetic field is an operator, which is polarized along the y direction. And then it has an amplitude, and now we can write as mu0 h bar divided, in omega m divided the volume of the cavity, Ls, and then Am, and the cosine of Km set, and the Hermitian conjugate. Okay? So the reason why I wanted to waste some time on writing this explicitly is so you see that now we have access to the self-adjoint operators, so the observables that correspond to the electric and the magnetic fields, which are the observable quantities in experiments regarding light and the electromagnetic field. And we have them as a function of annihilation and creation operators, okay? What else? Let me, yeah. So the other thing I wanted to say is I just give you a bit of notation that we might use, but you will see in books most of the time. So usually we divide fields. So you see that the field has a part that corresponds to the annihilation operator and a part that corresponds to the creation operator, so the Hermitian conjugate of this expression. So the part that corresponds to the annihilation operator, we usually call it in field theory A plus. Okay, so whenever you see that instead of A, I say A plus, what I mean is this is just the annihilation part of the field. And the field itself has to be self-adjoint, which means that you have to add the creation part. And the creation part, it's sometimes called A minus. So I know it's a bit confusing because you are calling plus to the annihilation, but this is because the plus is the one that corresponds in field theory to positive energy, okay? And the second part corresponds to negative energy. Maybe you have seen this, I don't know if you have studied the Dirac equation, but in the Dirac equation, it appears very naturally the concept of positive energies and negative energies, okay? And the negative energies are associated with creation operators. The negative energies are associated with annihilation operators, okay? And also with particles and antiparticles and so on. But okay, this is just some notation, so you are not lost when you see books. And this means that we can write the fields always as A plus A minus. And of course, the same applies to any other field, in particular to the electric field. So we will have an A plus that annihilates excitations, and an A minus that creates excitations. And the same with the magnetic field. Okay, then just 3 more things about this. The first thing is, look, something that I have done is that I'm writing these expressions, but I don't put any time dependence. Okay, why? Because when I'm writing these expressions, I am implicitly assuming that I am in the Heisenberg picture, sorry, in the Schrodinger picture. So operators do not evolve with time. If I would be in the Heisenberg picture, then the field would depend on time as well, because it's an operator. And now the annihilation operators would be time dependent, okay? And in particular, if you have the free electromagnetic field, the time dependence of these operators would just be the exponential of minus I omega t for the corresponding frequency, just like a harmonic oscillator. Okay, the second thing I want to say is the concept of photon. What are photons? So finally, after all these lectures, I can tell you what's a photon. A photon is just an excitation created by this part of the electromagnetic field. So it's an excitation created by the creation operators, okay? And then you see that you can create photons of different nature, in particular here, photons of different frequencies. So when you say that you apply the creation operator AM on the vacuum state that didn't have any photons, you are creating a photon of frequency omega m, okay? So then photons correspond to that, exactly. So Roy Glauber liked to say that this is kind of the mathematical view of what a photon is, but at the end of the day, we will also see in the course that a photon can also be something practical. In particular, a photon is a click that happens in a photodetector, okay? So these are 2 different definitions, a mathematical definition and a practical definition. So when you put a photodetector and you get a click, then that's also that will also be a photon, as we will see in the next chapters. And then the final thing I want to say is that, well, now that we have quantized electromagnetic field, we know that the electromagnetic field, in the absence of anything else, of any kind of material or source of electromagnetic field or anything, this is just equal the Hamiltonian, or is described by a Hamiltonian that will be equal to this in here. So this is just the Hamiltonian of each harmonic oscillator for each frequency omega m. So this slide in here summarizes the quantum theory of the electromagnetic field, at least inside an optical cavity. And I have removed, by the way, the factor 1/2 in the Hamiltonian, because it plays no role in everything that we are going to see in the course, but that factor 1/2 can play a strong role in some other contexts, like, for example, the Casimir force, which is something quite amazing that I want to just let you know very quickly. It happens when you take 2 conducting materials. So imagine that you take 2 conducting plates, and then you put them close together, okay? But they are not touching themselves, and you are doing it in vacuum. So there are no fields, you know, there are no classical fields, there are no electromagnetic fields that you are adding. You just put 2 plates, conducting plates, in vacuum. It's really amazing that some people started measuring in the lab that there is a force that appears between the plates, even when they are not touching each other, and even when there is no electromagnetic field around. And this force has to do precisely with these factors 1/2 that we get, and the fact that when we say that there is no electromagnetic field, what we mean is that there is no classical electromagnetic field, but if you are in free space, you always have vacuum fluctuations. So you have electromagnetic vacuum fluctuations because, as we have seen, the electromagnetic field is just a collection of harmonic oscillators, and the harmonic oscillator has vacuum fluctuations. And these vacuum fluctuations are enough to create a force, an attractive force, between these two plates, okay? Even if you would not expect it. I mean, no one would expect that you take two plates, you put them together without touching, and then suddenly they attract each other.
Sorry, the
Yes.
coefficient of E seems wrong. The omega
Why?
m should be numerator.
So let me just mark it down so later I remember. Okay. So we have like half an hour left, something like that. Yeah, so I think we can start the next chapter. In general, let me start talking about what we are going to call matter in quantum optics. So in quantum optics, it's very traditional or very normal to distinguish very clearly between the field, the electromagnetic field, and matter. So everything else will be matter. And what distinguishes matter from the electromagnetic field is something very simple. So we have seen that, so we have been studying the harmonic oscillator, which describes the electromagnetic field. And for this context, the most important thing about the harmonic oscillators and the electromagnetic field is that you can define a spectrum, an energy spectrum. Okay, actually, there is no arrow here because this axis means nothing. And in this spectrum, what we have seen, so let me try to do it properly. Is that the energies of the spectrum are uniformly distributed. So I mean that this gap between the energies is the same for all these transitions, okay? So this is what we will call a uniform spectrum. Then with, let's say, full generality, what is matter in quantum optics? Or what will be matter for us? So matter, like in practical terms, like in real terms, like physically what it is. So it could be atoms, it could be molecules, it could be solid state materials. So all these things are matter, of course, but what, let's say, what is the main property of matter for our purposes is the fact that the energy spectrum, it's not uniform. For example, it looks like this. I don't know, like E0, then you have here E1, then you have here E2, then you have here E3. So all these energy gaps, so this energy gap here that will have some frequency that we can call omega 10, this energy gap that has some frequency omega 21, this energy gap that has a frequency omega 3,2, all these frequencies are different, okay? So even this frequency here that has a gap or omega 20, for example, this is also different from, so all the frequencies in here are, let's say, different. And then we say that we have a non-uniform spectrum, okay? And why is this interesting? Because this, even if it seems that this is much more complicated than the harmonic oscillator, because at least in the harmonic oscillator, you have a simple structure for the spectrum. Even if this looks more complicated, at the end of the day, it will make it much more simple. Why? Because each transition, so each transition is unique. So this means that when I tell you, oh, please do something with this transition between only two energy levels, 1 and 0, you can really target it. And we will see exactly how to target it, okay? How we can work only with this transition and forget about anything else, okay? Anything else has a different energy transition, a different frequency, and therefore, we can really take care only of one specific one of them, okay? So this is what we will study in this chapter and in the following chapter when we study light-matter interactions. Here we will focus on the theory of matter, but we will essentially focus on how matter has very specific transitions. And in order to give you a concrete example that is very important in quantum optics, we will actually start by talking about the energy spectrum of atoms, okay? This will not be a course on atomic physics, so I'm not going to give you all the details about atomic physics and do all the quantum mechanics of atoms. This is a full course on itself with many courses later. There are many, many interesting things about atomic physics, especially if you start talking also about molecules or even solids. This goes crazy. You would need a whole year only studying the theory of matter in order to get deep into the quantum mechanics of this. But at least the quantum theory of simple atoms, you have already seen, and I will summarize in here, even if I will not later ask you to make any derivations about it in the exam or anything like that. But I think it's important that you understand a little bit about it, and that you see that the quantum theory of the hydrogen atom, for example, or even more complicated atoms that you have studied, appears actually in practical terms in many contexts in quantum optics. So then let me, in the next 10 minutes, just tell you the very basics of the hydrogen atom. And in the next lecture, we will start from there and we will go beyond the simple hydrogen atom. So let's start with the hydrogen atom that I'm sure that you have all studied in quantum mechanics. So this is the hydrogen atom. And essentially the hydrogen atom is probably the simplest type of matter that you can find because it consists on just a proton, which is interacting with an electron, okay? What are the degrees of freedom of this system? The degrees of freedom of this system, let's say that we don't care about the center of mass. So this proton and electron, they could be moving, like the center of mass could be moving around. We don't care about that. We are going to talk only about the relative motion. And the relative motion is determined basically by a vector that we call the relative coordinate, R, and it will be quantized. And on top of that, we have two more degrees of freedom, which are the spin of the electron and the spin of the nucleus, or in this case, the spin of the proton. Then the Hilbert space of the system, as I told you, the first thing when you are understanding a system is always to understand what is the Hilbert space that describes it. So this will be just the Hilbert space of an object moving in 3 dimensions, in particular the relative coordinate moving in 3 dimensions. And this we have already studied because we have studied the harmonic oscillator, which is an object moving in 1 dimension, but this is just the same 3 times, okay? So we have 3 directions, X, Y, and Z of motion. And so this is not a harmonic oscillator, but the space, the physical Hilbert space associated to this is the same. It's just the motional Hilbert space, the Hilbert space of motion, infinite dimension, and so on that we have studied. On the other hand, we have to add to here the Hilbert space of a spin 1/2 particle, which is the electron, which is, as you know from quantum mechanics, is two-dimensional. So we have spin up and spin down. And then we have to add the Hilbert space of the nucleus, which in this case of the hydrogen atom, which is just a proton. The nucleus is just a proton. Then it's also a spin 1/2, so a two-dimensional Hilbert space. So in total, we have a Hilbert space that have 3 times infinite dimension times 2 times 2, just for the hydrogen atom. Now, if I ask you what is the Hamiltonian of the system, which describes the system, then this is actually a very complicated question. The Hamiltonian is not as simple as you might think, but on a first approximation, we can always say, and this is called the Bohr approximation. We can always think that the most important contribution to the Hamiltonian will come from, first of all, just the free motion of the relative coordinate. So, by the way, I know that you know it, but just in case, we can even make an approximation that is even stronger, which is that the proton it just stays fixed. It doesn't feel any motion. It doesn't feel anything because it's much heavier than the electron. And then in such case, the relative coordinate is just the coordinate of the electron around the frame of the proton. But in general, we can just talk about the relative coordinate, and in the physics, it's equally simple. So then we have the kinetic term associated to that relative coordinate, which will be p squared over 2m, where m is the reduced mass. Which is just the mass of the electron if you go to the approximation that the mass of the proton is infinite, okay, compared to the mass of the electron. And this momentum is just the relative momentum. Again, the momentum of the electron in the approximation in which the mass of the proton goes to infinity. And then to this, so this is the kinetic term, we add a potential term. And what is a potential term is just the static Coulomb potential between a charge plus and a charge minus, which is just given by E squared divided by 4 pi epsilon 0. And the important part is that it depends on the, it depends inversely proportional with the distance between the two charges, okay? So this is what you know from electromagnetism or electrodynamics, okay? So to a first approximation, this is the basic Hamiltonian of the harmonic oscillator of the hydrogen atom. And what's interesting about this Hamiltonian, as you have seen in quantum mechanics, is first of all, of course, it commutes with the spin of the electron and the spin of the proton, because it doesn't depend on the spin, okay? And second, it commutes, so the Hamiltonian itself commutes with the square of the orbital angular momentum, and it commutes as well with the component set, for example. So we have to choose one of the angular moment of the orbital angular momentum. What is the orbital angular momentum? This is just R cross P, just the orbital angular momentum that you know from classical mechanics. And on top of this, we know that L squared commutes with LZ. So with the third component, let me maybe bring this away. So it's not on the way. Okay. I don't like this notation. Bring it here. So this is something that you know from your courses in quantum mechanics, that essentially the Hamiltonian commutes with L square and with LZ. And this is very nice because we have a three-dimensional space, which means that we will need three quantum numbers. For example, for the harmonic oscillator, we have a single quantum number because we were in one dimension. For the hydrogen atom, we will need three quantum numbers associated to this three-dimensional space. And we have three commuting operators, the Hamiltonian, the absolute value square of the orbital angular momentum, and the component set of the orbital angular momentum. So we will have these three quantum numbers, and then we will have the quantum number associated to spin of the electron and the quantum number associated to the spin of the nucleus. So all things considered, then the eigenstates of the hydrogen atom can be written in terms of 5 quantum numbers that I write in this way. So we have the quantum number associated to the Hamiltonian that I will specify in a second, the quantum number associated to L square, the quantum number associated to LZ that we call ML, and then the quantum numbers associated to the spin of the nucleus and the electron. And this, I will collect all of them into a single vector number called N, vector quantum number. And these are the eigenstates of the Hamiltonian. And the only important thing is that you remember that these eigenstates are eigenstates, so common eigenstates of all the commuting operators. In particular, when you apply the Hamiltonian to the eigenstate, you get an eigenenergy that depends on the first quantum number N. This quantum number N is an integer, positive integer, so a natural number. And the energy is specifically given by minus E0 divided N squared. And this E0 is called the Rydberg energy. And of course, it's an energy that depends on all the variables that are in the Hamiltonian, so on the mass, on the charge of the electron, on epsilon 0, and on h bar. So all these things appear in the expression of the Rydberg energy. I will not write it down, you have it in the notes. And in any case, you have proven this. So this thing, you have proven it in your quantum mechanics course. I hope I'm just reminding you. So on the other hand, if we apply L square to the eigenstates, then what we get is L times L plus 1, so something that it's order L square, h bar acting on the eigenstate. And what's important is that this L is restricted to 0, 1, all the way to n minus 1, okay? So when you fix n, so you say, I am working with the eigenenergy E1 or E2 or E100, this fixes what are the available total angular momenta that you can have for that specific choice of n, okay? On the other hand, if you apply LZ, then you get the quantum number ML. Sorry, this is h bar square because we have L square. So we need units of action square. Then LZ has ML h bar as eigenvalue. And this ML goes from minus L to L in units of 1. And then finally, we have SZ, which can be plus or minus 1/2. So that's the spin of the electron. And then let me just make slightly more space. So I don't write it too small. And then finally, we have the third component of the spin of the nucleus, Mi, which also, in this case, for the proton, so when the nucleus is only one proton, it has a spin either plus or minus one. Of course, I could also write that these are eigenstates of S square and I square, but that's something that it's fixed, like the quantum number associated to the spin of the electron is 1/2, and that's never going to change because that's a property of the electron. And the same for the property of the nucleus. You will never change the quantum number, the total spin of the nucleus within the processes that we are working on in quantum optics. And in particular for the hydrogen, you cannot change it because that's a property of the proton. You cannot change it. You would need to change the proton into another particle with another spin. So then essentially, these are the 5 quantum numbers that are important for the quantum theory of the hydrogen atom. And this is hopefully, as I said, just a reminder. Otherwise, I mean, this is a reminder for sure, but if you don't remember perfectly, I recommend you that you go to your quantum optics, quantum mechanics lectures and you remember how this appears, okay, all these things. And then in the next lecture, we will move to a bit of corrections to this Bohr approximation, and we will see how they can be very important, especially for quantum optics. And we will start checking the spectrum that comes out of this Hamiltonian and of this description. Okay, so I hope that you enjoyed this quick introduction to the hydrogen atom, and we will continue next week. So for now, just I say goodbye. I think that the Zoom session is finishing anyways. So I will see you next week, and I will